like 6 to 1 year. It simply says that we are given a bidirectional graph. As you know, it is an undirected graph with n vertices in which n nodes are there, and where each vertex is labeled from 0 to n minus 1. So the labeling is, if I'm saying I have n nodes, so I'm saying the label will be from 0 to n minus 1, where every edge is represented by a vector of vector, which is ui vi, saying it is an edge between ui to vi. And again, it's a bidirectional edge, ui to vi, and each vertex pair is connected by at most one edge, which means, okay, if I have a vertex pair, I will have one edge. I will not have multiple edges for the same pair, and I will have no self edge, like no vertex has an edge to itself, no self edge. Now, I want to determine if there's a valid path that exists from a vertex source to destination. So in this graph, I will have a source, I will have a destination. I need to know if there is any valid path I can go to, so that I can start from a source and I can reach my destination. Now, we have been given this edges array or vector of vector, and we have source, destination and stuff. We have to return true if I can reach from source to destination, and false otherwise. So if you just simply frame it, what it says, okay, you have a simple source. Again, I don't know, any source can be there. You have a simple destination. You just need to take any path, traverse any path and reach from your source. Take any path, traverse from your source and reach to your destination. That's what it wanted entirely. That's it. Now, if you want this, you hear the word traverse the graph. So I can just simply start my graph traversal from the initial node, which is source. Now we know that in the simple traversal of the graph, we have two and very famous algorithms, which is DFS and BFS. They simply traverse the graph, or to be more precise, they will simply traverse that specific component from which I will be starting off. What do you mean by that? What I mean by that is, let's say if I do a DFS or a simple BFS from node 0, then it will traverse and visit all the nodes in this component. That's it. It cannot go outside because it is a simple traversal which will traverse wherever he can go, wherever he can reach. So I realized, okay, I can simply do a graph traversal from a source node, and I will just simply have a check that was I able to reach my destination node, which means I'll keep a track of the visited, and I have a simple check if I was able to reach my destination node or not. Now you can simply see in this my source was a 0, destination was a 2, source was a 0, destination was a 2. I'll simply start my, again, in graph traversals, whenever, if you have already seen the bar graph series, we have already referred that whenever you have to traverse the graph and there is no boundation on level wise traversal, then it is highly and always recommended to use DFS instead of BFS. Why? Again, complexity wise, functionality wise, everything is same. It's just that the code is very small. So I always recommend to go by DFS. Again, I can say many approaches. Okay, you can solve this by DFS, you can solve this by BFS, you can solve this by DFS iterative, all that stuff. But no, nothing will change. Complexity will not change. Same exact same stuff. So solve it by DFS. Again, it can be solved by BFS also. You can say, okay, I've solved by DFS iterative. Okay, it's good for you, solve it, but that's not required. We can simply and easily solve by DFS because every of these will give us same complexity. Again, DFS iterative, I said. Cool. Now, when I say iterative, I mean just simply using a stack rather than actually recursive stack of actual DFS. Now, you can simply start your DFS from source, and then you can simply see if you are able to reach your destination or not. Same way, I have, let's say, starting my source from 0. This is my source. My destination is my 5. So when I will start my simple DFS from my source, I will be simply traversing all the nodes. Okay, all these are visited. DFS is done. Then I will just simply have a check. Was I able to visit my destination? No. It is still unvisited, which means that I cannot traverse from a source to my destination. That's the reason. Answer is false. Okay, so you realized that it's a simple DFS call, simple DFS traversal. Let's see the code. It's pretty simple. Firstly, I have a visited, because again, that's needed for both graph traversal also, and also to make sure that you have visited your destination or not. You will have your graph. Simply, you can initialize with your vector of vector. As you can see, simple adjacency list. Now you went on to all the edges, and for every edge you grabbed the node U and V, then you plotted a undirected graph, as in like bidirectional graph or edge between U and V. Then you started your DFS from the source node, and it's a simple, short and simple DFS code that if something is visited already, return. If not, then visit that specific node and then go on to child. If the child is not visited, then do the DFS of the child. Again, if you skip this line, still it will work because you are having a check as soon as you start your DFS call. Now, as soon as this entire DFS is done, you will see that either you will visit the destination or not visit it, considering if your destination is in the same component as that of your source. If it is, you will visit it. If not, then you will not visit it. If not, then you will, again, even if you visit or not visit it, you will simply return that were you able to visit your destination or not. And that's your answer. Now, the prime part is, what is the time complexity of this problem? One thing is very simple. I know that I am iterating on all the edges. So for sure, O of M will, again, if I consider I have M edges and N nodes. So O of M is for sure there, right? Now, this source, as you know, that because of my visited, every node will be visited exactly once, right? Okay. So I know that I will visit every node exactly once. Okay. So O of N is for sure here. Right, and again, even if I visit every node exactly once, still I might and I would be iterating on the edges. For example, if I have a graph like this, so let's say I start from my source, then I will simply go on to this specific edge and then I will visit this node. Again, let's say this is visited, then I'll go on to this edge. Let's take the color, this edge, I'll visit it. Then I'll visit this node. Okay, I'll visit this node. Then I'll go to, let's say, this edge. I'll visit this node. Then I'll go to this edge. I'll visit this node. Then I will be going to this edge and checking. Okay, it is not visited, but still I went on to this edge and did a check. Okay. Then, okay, this edge is also visited, but when I checked the other side of the node, it was like already visited. So I just came back. Then again, the same way you go, sorry, no worries. Then you did one thing, that you went on to this edge again, like to have a only check. Like you will go on to child. If you check the child is visited, then you come back. Okay, I cannot go there. If it is not visited, then you go. So I went on, oh, it's already visited. Okay, come back. But still, you went on and checked. Then same way, you will backtrack. Now you are here. You still go and check your child. Oh, it's already there. Okay, come back. But still, you are checking your child. So it is nothing but O of N plus M. Cool. Now, so time will be O of N plus M, and for sure, technically, if we say the space required will be simply saying that I went on to all the nodes. So my recursive stack will just go on to all the nodes of my entire tree or graph, which means first this node, then this node, then this node, then this node. Then it will go and check, but it cannot go to other nodes. So it will come back. So my space will be just O of N. Cool. Now, if I ask you, although BFS, DFS, everything looks same, exactly same, and I will highly recommend that you should go by this approach itself. Is there any other approach? Maybe, maybe not. Let's see. So if you had seen, to find the candidate component, there is another approach called as DSU. Now, which is disjoint set union. If you had not understood what is DSU or how to solve DSU, how to write the code of DSU, most efficient code of DSU, please go and watch this video in which I have explained very deeply what DSU is, how to use it, how is the code written, and what is the snippet we use. We use the most optimal DSU snippet. Now again, I will simply have pasted the exact same DSU piece of code. DSU is disjoint set union. It simply says that I will get two nodes, I will union them, and we'll say, okay, now they belong to one component. Again, I get, let's say, another node. I will, let's say, I have another two nodes. I will again union them. Let's say I have to join these two nodes. Again, I will just union them. So now they belong to one component, and this union is actually in the rank wise order, and it's very efficient union. So I realized, bro, that's awesome. the benefit of this union is, see, this portion in which you initialize, it's nothing but O of n. It's nothing but O of n. This find function, again, its amortized complexity is again O of 1. You might see like Aryan, it's recursion. But still, if you go and watch this video, you will realize that that's the beauty of DSU. Its amortized complexity is actually linear. It's just O of 5 or O of 6 or something. So it's O of 1. And the strange part, this union is also O of 1. So you realize, okay, your DSU looks awesome. It's just that initialization will take some time and then everything is just constant. So you went on and did exact same stuff. You went on and initialized your DSU. It's O of n. Then you actually went on and iterated on all the edges. Again, it is O of m, right? And then you will simply, again, as soon as you are doing O of m, you are doing a union, which is again a O of 1 operation. Then you will just simply go and find, again, you just have to check if both of the source and destination belong to same component or not. Whenever component picture comes in, DSU is the word which you must think. I'll not recommend this to write in a contest just because of the reason that this is a boilerplate code which you have to write, or you can copy paste, it's good. If not, if you are writing it from scratch, then it's a big task. And that's the reason in the beginning I told you this is not an easy problem, considering you also think about union find. Now again, if I come back, then it will be simply saying, okay, DSU of source, which means I'll find the component of the source. This DSU.find nodes will give in which component, or basically what is the parent, what is the super parent of my source node, and what is the super parent of my destination node. If both the parents are same, which means they belong to the same connected component. If that's the case, return a true. If not, return a false. That's how I can simply do it. Now, for short, as you can simply see, the time will be O of n plus m, right? And as you can simply see, the space used will be just O of n. Space used will be just O of n. And that's again, on paper, the complexity is same, but you will see that DSU code will have a better runtime because of that, how it performs, how it, like, anytime you are just having simple check or fun check rather than going on to entire DFS and stuff. In general, DSU performs a bit better than actual DFS. And again, this is not the best example to test the capabilities of DSU. If you want to test the capabilities of DSU, I'll go and highly recommend just go and watch this video, or write DSU by Aryan Mittal. You will get the video on YouTube, and then you can see many other problems in which you can find the actual capability of DSU. Cool. This was it. Again, I told you this approach just because it's a bit different than BFS or simple DFS. Although you can solve this problem by 4 approaches. DFS, I told you. BFS, because simply it's also a traversal. DFS iterative, that's bullshit thing, but yeah, you can do it. And lastly, DSU. Cool. Bye bye. Take care. Again, any problem which simply involves component, DSU can come in, but this is a very easy problem for DSU. DSU is not built for this problem. Cool. Bye bye. Take care. Because DFS can simply handle it. Bye bye.